Hello friends, I am Professor Rajendra Koranne from my YouTube channel Teach Easy. In this video, I will be explaining the design of one-way simply supported slab. Now, all the steps involved in the design of one-way simply supported slab will be explained with the help of one problem. Whatever important steps and important provisions for the design of one-way slab will also be explained with the help of the particular clause given in IS 456/2000. Therefore, I request you to please completely view the video so that you will understand each and every step. Now let us see the problem of one-way simply supported slab. Now the problem is design a one-way slab for the following data. The span is 3 meter. The slab is supported on 230 mm thick walls. The live load is 4 kN per meter square and the weight of the floor finish is 1 kN per meter square. The grade of concrete is M20 and the grade of steel is Fe415. Take modification factor as 1.4. This is a problem which is asked in MSBT examination for diploma for 6 marks. Now we will see how to solve this particular problem. Now let us first list out the data given in this particular problem. Now let us see what is the data given. Now first one, the span is given as 3 meter. This is a clear span L0 equal to 3 meter. Now it is also given in the problem that the slab is supported on 230 mm thick walls. So BS, what is BS? Width of support is 230 mm. Then the intensity of live load is given 4 kN per meter square. Then floor finish is given, weight of floor finish, that is 1 kN per meter square. Then the grade of concrete is given, so FCK is given. It is M20, therefore FCK is 20 Newton per mm square. Grade of steel is also given, Fe415, so Fy is equal to 415 Newton per mm square. Similarly, modification factor, value of modification factor is also given, that is 1.4. So this is the data given. What is the required thing? You have to design the slab, means you have to find out the depth of the slab, you have to find out the reinforcement of the slab, and you have to apply the required checks as per IS 456. Okay, so let us see how to solve this particular problem. Let us see the first step. Now the first step is to find out the trial depth. Trial depth. Now for finding out trial depth, we will have to first take down the value of Lx, that is whatever effective length is first available. So Lx here we will see, this is a one-way slab, only one span is given. Lx is equal to L0 plus Bs by 2 on one side plus Bs by 2 on another side. Therefore, you will get Lx is equal to 3000, 3 meter means 3000 plus Bs by 2 plus Bs by 2 will become Bs, that is 230, and hence the Lx will become 3230 mm. Okay? Now, we have to find out the trial depth of the slab, and for that purpose, we will take the help of deflection criteria, that is basic L by D ratio. And what is that? That I will show you now. This is page number 37 of IS 456 2000. Here you can say the vertical deflection limits may be assumed to be satisfied provided that the span to depth ratios are not greater than the following values: cantilever 7, simply supported 20 and continuous 26. Okay, so we can say that from page number 37, clause 23.2.1a, of IS 456 2000 for simply supported slab or beams. The basic value of L by D ratio is equal to 20. Now we want to find out trial depth. So what is trial depth? The effective depth small d is equal to Lx upon L by D basic multiplied by modification factor, which is given in this particular problem. So this will be equal to, let us take in mm, 3230 divided by, what is the value of L by D basic ratio? 20. What is the value of modification factor, which is given as 1.4? And you will find that this value comes out to be 115.35 mm. 115.35 mm. Say 120 mm. Now this is effective depth. So we know that overall depth which is denoted by capital D, is equal to effective depth plus effective cover. What is effective cover? Effective cover okay. Now let us see what is effective cover. Effective cover is equal to nominal cover plus half the diameter of the bar used for reinforcement. Now for nominal cover, again we will see page number 47 of IS 456-2000. Nominal cover to meet durability requirements for mild exposure, it is 20 mm. Nothing is given in the problem that what is the type of exposure, so let us assume it as mild. So for mild exposure, minimum nominal cover is 20 mm. And in the notes it is given that for main reinforcement up to 12 mm diameter bar, for mild exposure the nominal cover may be reduced by 5 mm. Now definitely our diameter of the bar will be less than 12 mm, so you can reduce this cover by 5 mm. So nominal cover may be taken as 20 mm. Okay, 20 minus 5, that is 15 mm. And if I say that diameter of the bar used is 10 mm, then 15 plus 10 by 2. Therefore, the effective cover will be 20 mm. And therefore, we can say that overall depth of the slab is equal to 120 mm. That is the effective depth plus 15 mm, that is nominal cover, plus 10 by 2, that is 20 mm, and hence this will be 140 mm. So in this first step, we have calculated the effective depth and the overall depth of the slab. So let us go for step number 2. Now step number 2 is an important step of load calculations. Load calculations. Now, this is a one-way slab, we already know. So if I say that this is LX, the slab is spanning in this particular direction, that is, the load will be supported or transmitted in this particular direction, and we are considering, the loads will be considered for 1 meter wide strip of the slab. So this strip is 1 meter wide. Okay. So we will be calculating the loads for 1 meter wide strip. Okay. Consider one meter wide strip. Okay. So first one, self weight of slab, self weight of slab. What is self weight of slab? Self weight of slab will be unit weight of concrete, that is 25 kilonewton per meter cube, into effective depth, overall depth d in meter, into 1 minus 1 meter wide strip, that is 1, and hence this value will be 25 into d in meter, that is, what is d? 140. So in meter it is 0.140 into 1, which comes out to be 25 into 1.4, that will come out to be 3.50 kilonewton per meter. Okay, so this is self weight of the slab. Now second one, live load. Now live load can be calculated as intensity of live load multiplied by 1, because we are considering 1 meter wide strip. Now intensity of live load is given as 4 kilonewton per meter square into 1 will become 4 kilonewton per meter. Now third one is weight of floor finish, self weight of floor finish. So that is also intensity of self weight is given multiplied by 1. So it is, how much it is? It is 1 kilonewton per meter square multiplied by 1 is equal to 1 kilonewton per meter. If you add the three, you will get total weight W is equal to 8.5 kilonewton per meter. Okay? Now, in every type of design of slab, you will have to calculate the load, and for that purpose, if you use this formula, you can save the time. So this is W, and what is a design load or ultimate load? Design load will be design load WD is equal to 1.5 into W, that is 1.5 into 8.5, okay, which comes out to be 1.5 into 8.5, which comes out to be 12.75 kilonewton per meter. Now this is the design load. Okay, so now this step is very important step, load calculation, which is required in every design of any type of slab. So here I will write a standard formula with the help of which you can calculate it very easily and you can save the time in exam. Design load which we denote by WD is equal to 1.5 because we are making it ultimate into bracket. Okay. What is the self weight of the slab? 25W plus live load plus floor finish. So this I have told you to explain the particular thing. In exam, once you understand it directly, you can use this particular formula, okay, with the help of which you can find out design load directly. So this is the important formula to find out the design load directly. Do you follow this? Okay. Now once you find out the design load, the next step is to find out the design moment. Okay. So let us go for step number 3. Design bending moment. BM. Now for design BM, this is simply supported slab WL square by 8, so that effective length is required to be calculated. Okay, and for that purpose again I will show you the clause number 22.2.a, where it is given that for simply supported slab or beam, the effective span of a member that is not built integrally with its support shall be taken as clear span plus the effective depth of the slab, or center to center distance between support, whichever is less. So let us first find out this effective span. Okay, so I have shown you what is that from page number 34 of IS 456. Clause I have shown, so it is not necessary to remember the clause. Once you know the page, you can see it. Okay, so as this is the first example on design of slab, I am showing everything. In the next example, I will not be showing this. Clause number 22.2.a. Okay, so what is that? Effective span is equal to clear span plus effective depth and clear span plus BS, that is width of the support, that is center to center distance, whichever is less. Therefore, LE is equal to, first I will calculate L0 plus D. Okay, so what is L0? L0 is 3 meter. What is small d? 120 mm, that is 0.12, which comes out to be 3.12 meter. And the second one is clear span plus width of the support 0.23, BS by 2 on one side, BS by 2 on second side. So this is 3.23 meter. Whichever is less, you can very easily see that this is lesser of the two. Therefore, we can say that what is the effective span? Effective span LE is equal to 3.12 meter. Do you understand? Once you calculate the effective span, you can find out the design bending moment. Okay? So let us proceed further. So we will be continuing the step number 3. Okay, effective span is calculated. Therefore, I will now calculate design bending moment. Design BM, which we denote by MD. MD is equal to, as it is simply supported, it will be WD into LE square upon 8. Put all the values. What is WD? WD is 12.75. LE is 3.12 square divided by 8, and you will get this value of design moment as 15.51 kilonewton meter, which is equal to 15.51 into 10 raised to 6 Newton mm. So this is the design bending moment for which we have to design the slab. Now let us go for step number 4. Now step number 4 is one of the important steps. Check for D for BM. Now what is the meaning of this? Now the depth of the slab, that is 120 mm, which we have taken, that is the depth for deflection criteria using basic L by D ratio. Now bending moment is calculated. What is the depth required to resist the bending moment? It is also important to find out, and for that purpose this D which we have provided or calculated, that is 120 mm, whether it is sufficient to resist the design moment of 15.51 kilonewton meter or not. For that purpose this step is taken. Okay. Now we are using Fe415. Okay. So in this step, to calculate the value of D for BM, we have to equate this design bending moment with ultimate limiting moment of resistance, that is mu lim, and we know that value of mu lim for Fe415 is 0.138 FCKBD square. For Fe415, mu lim is equal to 0.138 FCK B into D square Newton mm. Okay, so we will equate the two, that is MD. So this is Newton mm, so we have already converted. So 15.51 into 10 raised to 6 is equal to 0.138. FCK is 20, B is 1000, and D we have to calculate. With the help of scientific calculator, if you solve this for D, you will get the value of D is equal to 74.96 mm. Mind well, this is the value of D required to resist, yes, the design moment MD. Now you can very easily see that the effective depth required to resist the design moment is 74 for 96, and the D which we have provided is 120 mm, so it is definitely more. So this is okay. So you can write as D provided is equal to 120 mm greater than 74.96. This is okay, means it is safe. Not only okay, if you calculate the value of mu lim taking value of D as 120 mm, you will find that mu lim is greater than MD, or you can say that MD is less than mu lim. It means that the section is under reinforced. So this is important step in which you have to show that whatever values of depth and all these things you have taken, definitely the section is under reinforced. Okay. Now, as you have checked the value of D for bending moment, the next step is important step to calculate the reinforcement. Now we already know that for one-way simply supported slab, the load on the slab is transmitted in one direction only on two opposite edges. Therefore, along the shorter direction, the reinforcement bars is laid first, that are known as main bars, and over those main bars, the distribution bars to resist the thermal stresses and stresses due to creep and shrinkage, they are provided, which are known as distribution bars or distribution reinforcement or distribution steel. Okay, so let us first go for Mainsteel. Main reinforcement. Now, here we know that the section is under reinforced, so main reinforcement can be calculated by that cinemascopic formula. And what is that? So I will write here AST, that is area of tension reinforcement. As it is Mainsteel, I will write M is equal to, this is very important formula, useful to find out the reinforcement in almost all designs. Okay, in some another video I will explain you how that formula is obtained. So 0.5 FCK upon Fy into bracket 1 minus under root of 1 minus 4.6 mu or MD. MD means design moment, that is ultimate moment, upon FCK B into D square, bracket complete, this bracket also complete, multiplied by B into D. This is the formula to calculate the area of reinforcement for under reinforced section. So look here, AST main is cross-sectional area of main reinforcement, FCK is grade of concrete, Fy is grade of steel, MD is design moment, FCK is grade of concrete, B is the width 1 meter wide, D is effective depth, and by this formula we have to calculate this. Okay, so let us continue. So we will go on substituting these values. So ASTM, that is main, is equal to 0.5, value of FCK is 20, divided by Fy is 415 into bracket. Right, systematically it will eliminate the possibility of error. 1 minus under root of 1 minus 4.6 MD, that is design moment, is 15.51 into 10 raised to 6. This is very important because we have to substitute all the values in Newton mm. So if you forget to multiply by 10 raised to 6, the answer will be wrong. Divided by FCK, that is 20. B is 1 meter, that is 1000 mm. And D square, D is 120. Square of that. Rectangular bracket complete into B into D. So again B is 1000 into D is 120. Okay. So this is the cinemascopic formula, which is very, very important, and you will find that if you calculate it, you must have a practice to calculate this. It comes out to be 383.61 mm square. Okay. Now, this area of steel which we have calculated shall not be less than the minimum area of steel. Now, what is the minimum area of steel? That is given on page number 48 of IS 456. So again see here IS 456 2000, minimum reinforcement. The Mainsteel reinforcement in either direction in slab shall not be less than 0.15% of the total cross-sectional area. However, this value can be reduced to 0.12% when high strength deformed bars or welded wire fabrics are used. Now here we are using Fe415, that is high yield strength deformed bars. So it will be 0.12% of the total cross-sectional area. So look here what I am showing. See, look here. Here I have shown you that particular clause. Okay. So I will say AST minimum is equal to 0.12% of B into capital D. So here you will get it as 0.12, B is 1000 D is 140 mm divided by percent means 100, and you will get this as 168 mm square. Okay, now you can see that minimum area of reinforcement is 168. The area of reinforcement which we have calculated by cinemascopic formula is 383. So you can very easily see that this is not less than. This is important, not less than. Okay, Ast minimum. Therefore, this is safe or okay. This is, what is this? This is the area of main reinforcement. Okay, now this is the area. We have to find out what will be its spacing, and for that purpose, let us say that using 8 tor bars. What do you mean by 8 tor bars? HYSD bars of diameter 8 mm. Okay. The spacing is calculated as spacing is equal to 1000 into small AST. What is small AST? That is the cross-sectional area of one bar upon capital AST main. That is, this is what we have calculated, and we know that for 8 mm diameter bar, what is small AST? For 8 tor bar, small AST is equal to 50.27 mm square. Therefore, spacing is equal to 1000 into 50.27 divided by 383.61. Okay, which comes out to be 131.04 mm. Now, mind well, we have to check this spacing for maximum value of spacing, and for that purpose, if you see page number 46, okay, clause number 26.3.3 B. So 1, you can see that the horizontal distance between parallel main reinforcement bars shall not be more than 3 times the effective depth of solid slab, or 300 mm, whichever is less. Similarly, for distribution steel, that is given the horizontal distance between parallel reinforcement bars provided against the shrinkage and temperature, that is distribution steel, shall not be more than 5 times effective depth of solid slab, or 450 mm, whichever is less. Okay, so for main steel it is 3D or 300, whichever is less, and for distribution steel it is 5D or 450, whichever is less. Okay, so let us apply the check for maximum spacing. So first one, what is first? 3D. We know the value of D is 3 into 120 So it will be 360 mm. Okay, and second is 300 mm. Whichever is less, so you can very easily understand the lesser value of the two is the second value. And very important thing, this spacing which we have calculated is not greater than this value, so is not greater than 300 mm. Therefore, it is okay. So in this manner, we have calculated the main reinforcement. Okay. Now, in this main reinforcement, so I will give the judgment. Hence, therefore, provide eight tor bars at 131. I will round down 130 mm. Center to center with, this is important, alternate bar bent up at a distance of 0.1 Lx. That is, what is Lx? 3230 by 10 means 320 mm from face of support. So this is design of main reinforcement is complete. Now let us see how to calculate the distribution reinforcement. That is step number 5B. In part A, we saw how to find out the main reinforcement. Now here, distribution reinforcement. Now distribution reinforcement is provided along the longer span over the main reinforcement. This reinforcement is provided to resist the temperature stresses and the stresses induced due to creep and shrinkage. Okay. Now how much distribution reinforcement is provided? We know that previously I have shown you the distribution reinforcement, that is how much it is provided. So I will be saying that using 6 mm pi. What do you mean by pi? Mainsteel bars. As we are using Mainsteel bars, then we can say that area of reinforcement for distribution is taken as 0.15 percent. Okay, so that I have shown you from IS 456 2000 on page 48. So 0.15% of the cross sectional area, that is B into D. Okay, so which you can calculate as 0.15 into B is 1000 into D is 140 and divided by 100 for percentage, which comes out to be 210 mm square. Okay, now this is area. Now 210 mm square. Now what is the spacing? Spacing is equal to 1000 into small ast upon capital ASTD, D for distribution, which is equal to 1000 into 6 mm bar cross sectional area is 28.27 divided by AST distribution is 210, and this spacing comes out to be 134.64 mm. Now, like Mainsteel, we will have to apply the check for maximum spacing for distribution bars also. From page 36, I have shown you from clause number 26.3.3 B2, what is the maximum spacing? That shall not exceed the lesser of the two. The first one is 5D and 5 into D comes out to be 600 mm, and second one is 450 mm, lesser of the two. So from this we can very easily see that the lesser value of the two is 450 mm, and this particular spacing which we have calculated is not greater than the specifications 5D or 450 mm, whichever is less. Therefore, this spacing is also okay. And now you can say that provide yes 6.5 bars as distribution reinforcement. Steel at spacing of 130 mm center to center over main bars. This is important. So in this manner, we have calculated the main reinforcement and the distribution reinforcement also. So as far as the problem of 6 marks is concerned, this much is okay. Only additional thing you have to do is you have to draw the cross section. Okay. Before that, we will go for summary. So to summarize with, what are the things? The first one, effective depth is 120 mm. Second one, overall depth, capital D, is 140 mm. Third one, main reinforcement, what is main reinforcement? We have provided is, yes, 8 tor bars at a spacing of 130 mm center to center, and the distribution steel this is 6.5 at 130. This has nothing to do with this 130. For this particular example, it has come same. It doesn't mean that the spacings are same. C/C. Let us draw the cross section of the one-way slab. Now this is a one-way slab whose effective depth is 120 mm and overall depth is 140 mm. So let me correct it. It is 140 mm. Then the clear span is 3 meter. Width of support is 230 mm. Now this blue line is the main reinforcement, 8 tor bars at 130 center to center, and these red dots are distribution steel 6.5 at 130 center to center. So this is the cross section of one-way slab showing reinforcement details. Now after drawing this cross section of the shaft, slab, this particular problem is over. Now as far as 6 marks are concerned, this is more than sufficient for a diploma level examination. But to understand the procedure of application of checks for shear and bond, I am continuing this problem, but for 6 marks this is more than enough. Okay, so only in this particular slab I will explain you the steps involved in check for shear and bond. Okay, so let us go for the next step. So 5 steps we have already done. Okay, so let us go for step number 6. That is check for shear. Check for shear. Now, we know that this simply supported beam carries a UDL, that is a design load of 12.75 kilonewton per meter over an effective span of 3.12. So what is maximum shear force? So maximum shear force VU which is equal to WD into LE upon 2. Okay, so this will be equal to WD is 12.75, LE is 3.12 divided by 2, which comes out to be 19.89 kilonewton. Okay, now according to clause 40.1 of IS 456 page 72, nominal shear stress tau V is VU upon B into D, where VU is maximum shear force, B is width and D is effective depth. Okay, so this clause I have shown to you. So nominal shear stress shear stress, which we call it as tau V equals to VU divided by BD. Okay, so we will substitute the value of VU 19.89. This is kilonewton, so into 10 raised to 3 will be Newton. Okay, divided by B is 1000 and D is 120. If you calculate this, this will come out to be 0.17 Newton per mm square. This is nominal shear stress. Okay, now depending upon the area of reinforcement provided, we have to find out the shear strength of concrete. Okay, so first we will have to calculate AST provided. AST provided means whatever main reinforcement we have actually provided. AST provided is equal to 1000 into area of 1 bar upon main bar, definitely, upon spacing of main bar. Okay, therefore it will be 1000. Main bars 8 mm tor we have provided, so area of 1 bar is 50.27 divided by spacing is 130. So if you calculate this, this will come out to be 386.69 386.69 mm square. Now from this we have to calculate percentage PT, that is 100 into AST upon BD is equal to 100. Now mind well, here AST is the reinforcement bars which are on tension side extended up to the end. Now we know that half of the main bars are bent up, so only half of the bars are available at the bottom. So what is AST available at the bottom? 386.69 divided by 2, that is half area is available. B is as usual 1000 and D is 120. So if you calculate, this comes out to be 0.16%. Okay. Now from this percentage PT and grade of concrete, we have to find out shear strength of concrete. Now look here, for that purpose, see here, this is table number 19, in which you will find that here there are percentages and this is M15, M20. So we want to find out for M20 and 0.15, this is 0.16 is very close. Okay, so I will take it as 0.28. Okay, so this is from table number 19 of IS 456 2000 on page number 73. Okay, so what you are going to write now? For M20 and 0.16% steel, shear strength of concrete, that is tau C, that we have calculated from table number 19, and it comes out to be 0.28 Newton per mm square. Now once again, this tau C shall not exceed tau C max. Okay. Now for that purpose, let us find out the clause from page number 73. You can see here from page number 73 and table number 20, maximum shear stress tau C max for grade of concrete M20, this is 2.8. Therefore, you can very easily see that this particular tau C is not greater than tau C max. Therefore, OK, not greater than tau C max. If it is greater than tau C max, then you will have to revise the section. Therefore, this is definitely OK. Okay, tau C must be less than tau C max. Now what we understand from this? This is the shear stress actually induced. Okay, 0.17. Okay, and this is the shear stress resisted by the concrete. Then as this is a slab and thickness of the slab is very small, this strength again is multiplied by the constant K, okay, and you can say that, again we will go on page number 72. See, look here. Design shear strength of concrete for solid slab. Design shear strength for concrete slab shall be taken as K times tau C, where K has the values given below. It depends upon the thickness. If the thickness is 300 or more, it is 1. As the thickness reduces, this value increases, and for the value 150 or less, it is 1.3. Therefore, in this case, value of K is 1.3. Okay, so we will say that for 140 mm thick slab, K is equal to 1.3. Therefore, K times tau C, that means this tau C multiplied by K, okay, will become 0.36 Newton per mm square. Okay. Now you can very easily see that as tau V. What is tau V? Tau V is 0.17. What is K times tau C? 0.36. So as tau V is less than K times tau C, it means that the slab is safe in shear. Okay, so this is how we have applied the check for shear. Now the check for shear, almost 99% slabs are very safe in shear. Therefore, it is not necessary to check the slab for shear. So now let us take the check for bond or check for development length. This is 7th step, check for development length. Check for development length. Now let us see how to go for check for development length. Now first, according to clause number 26.2.1, we will have to calculate the development length required. LD is equal to phi into sigma s upon 4 times tau BD, where phi is the diameter of the bar, sigma s is stress in the bar, which is taken as 0.87 Fy. So according to this clause number 26.2 of IS 456 2000 from page number 42. Okay, so let us see what we get in this case. Okay, so LD required. How do we calculate LD required? LD required is calculated as 0.87 Fy. This is sigma s upon 4 times tau BD, into phi. Now here 0.87 Fy this is upon 4 times tau BD into phi. Okay. So Fy we know. Now what is tau BD? Now for this tau BD, again we will have to see page number 43, clause number 26.2.1. This for a grade of concrete, tau BD is given. You can see here our grade of concrete is M20, so this is design bond strength is 1.2, but this is for plain bars. Ours are deformed bars, so you will have to increase it by 60% because it is in tension. If it is compression, you will have to increase it more by 25%. But here the bars are in tension, so you will have to increase it by 40%. Okay, so what will be tau BD in this case? Tau BD will be equal to, for Mainsteel bars in tension and for M20 concrete it is 1.2, and for HYSD bar we are using Fe415. You will have to increase it by 60%, that is 1.6, which comes out to be 1.92 Newton per mm square. Okay. Now let us calculate this LD required. 0.87 Fy means 415. Phi means main bars are of 8 mm diameter divided by 4 times tau BD we have calculated, it is 1.92, and you will come to know that this LD required, development length required, comes out to be 376 mm. This is development length required. Now let us see what is the development required. This is simply supported slab. So how much development length is available at the support, that we have to see now. Okay. Now for that purpose we will have to see page number 44. Okay. Page number 44. So look here. From page number 44 of IS 456, at simple supports at the points of inflection, positive moment tension reinforcement shall be limited to diameter such that LD computed for 226.2.1 does not exceed. Now this is calculated as M1 upon V plus L0, where M1 is given as moment of resistance of the section, assuming all the reinforcement at the section to be stressed to Fs, then 0.87 Fy, then V is given, L0 is given, phi is given. But it is important to note that the value of M1 upon V in above expression may be increased by 30% when the ends of the reinforcement are confined by compressive reaction. Now what do you mean by confined by compressive reaction? Now you can see here, this is the slab, so this is the end. Here also there will be some wall, so this end will be confined by the compression reaction from down as well as from up, and hence this can be increased by 30%, and hence it will be 1.3 M1 upon V. Okay, so how to go for this? So look here. LD available near support is equal to, just now I have shown you, 1.3 M1 upon V plus L0. L0 is additional extra anchorage which is provided at the end of the bar. Okay. Now, what is M1? M1 is moment of resistance of the cross section. Okay. Now, here we know that in case of slab, half the bars are bent up near the support. Therefore, as half the bars are bent up for slabs, this is for slabs only. For beam, we will have to calculate it. For slab, M1 is taken as MD, that is what is design moment, divided by 2, and our design moment was 15.51. So 15.51 divided by 2. Therefore, this comes out to be 7.76 kilonewton meter. Okay. Then we know that what is V? V is the value of shear force. Okay. Which we have already calculated, and that is 19.89 kilonewton. Now, let us say that L0 is 0, no extra length we have provided. Then LD available will be equal to 1.3 M1. What is M1? 7.76. Okay. Kilonewton meter divided by 19.89. This is also kilonewton. Okay. L we have assumed as 0. Okay. So what we will do? We will convert it in Newton mm, and for Newton mm 10 raised to 6, and this we will convert in Newton, that is 10 raised to 3. So this is 10 raised to 6, 10 raised to 3 plus L0 is 0, which comes out to be 508 mm. As now you can very easily say that as LD available is greater than LD required, slab is safe for bond, flexural bond. Okay, so this is how we have applied the check for bond also, and with this we have completed the problem of one-way simply supported slab. Now again I will repeat one thing. Now as far as the problem in the examination is concerned, it is not necessary to apply the check for shear, check for development length. You can stop after drawing the sketch showing reinforcement details. Okay, so here I will stop, and in the next video I will be solving the example of two-way simply supported slab. Thank you.